Okay, let's just go through the first one, just to make sure we're all okay. So we've been given that z equals 2 cos of pi by 6 plus I sine of pi by 6. Okay, so you're happy that 2 is the modulus, it's the length of that line, and theta, the argument, is pi by 6. Okay, it's what angle we've moved through from the positive real axis anticlockwise. And we have been asked to find z to the power of 3. Okay? So just very simply then, we've said, right, we have stretched the complex plane by a factor of 2 3 times. In other words, we've gone stretch by 2, another stretch by 2, and another stretch by 2. So in total, we have stretched the plane 2 to the power of 3 times, or 8 times. Okay? But we've also rotated the plane by an angle of pi by 6 3 times. So we've gone pi by 6, then another pi by 6, then another pi by 6. So in total, we've gone 3 lots of pi by 6 in each of the i's and sine directions. So 3 pi by 6. Okay? So that's the basic raw form. You notice I'm just simply using the formula there. Okay? So all I need to do is just tidy this up now. So 2 to the power of 3 is equal to 8. And what can I do with my cos of 3 pi by 6? How could I root? Good, exactly. The 3 and the 6 cancel. Plus I sine of pi by 2. Is that okay? Yeah? Okay, fine. Let's have a quick look at question 2 then. Well, actually, no, because question 2 is very, very similar. Let's have a go at question 3. So question 3, we're still given a complex number, but it's not in this form. It's not in polar form. It's given in Euler form. So we have 2 root 2 e to the pi by 4i. Okay? E to the pi by 4i. But it still works. Like, my modulus is 2 root 2, so I'd still stretch it by 2 root 2 however many times I'm going. And then this is my argument, pi by 4, so I'm moving through an angle of pi by 4 for, what is it, z to the power of 6. So I'm stretching the complex plane 2 root 2 by 2 root 2 6 times. So it'd be 2 root 2 all raised to the power of 6. Okay? And then I've got e, that's my argument, so I'm moving through an angle of pi by 4 that many times, 6 times. So I've gone 6 times by pi by 4, lots of I. Is that okay? It's the same kind of idea as this. Exactly the same kind of idea, just written in a different form. And then I go through and I tidy. So, okay, 2 root 2 raised to the power of 6. Well, 2 to the power of 6 is 64. Root 2 to the power of 6 is 8. So 64 times 8, what's that? 512? Maybe? Can you check? And then that would become e to the power of 3 pi by 2. Lots of I. Do you agree with 512, by the way? Yeah, good. Okay. So you're happy that working with it in Euler form is exactly the same, pretty much, as working in polar form. It's still the same kind of idea. Okay, so it still extends. Okay, now have a look at question 6, for example. So question 6, we're not given in Euler form, and we're not given in polar form. We've got z is equal to 5 minus I. And we've been asked to find z to the power of 2, z squared. Okay. Now here's the issue. Here's the issue. Because this isn't in polar form and Euler form, we don't know what the modulus is and we don't know what the argument is, which means we need to find it. Okay. So we need to rewrite this in either polar or Euler form, basically. So first of all, I need to find my r. I need to find my modulus. Okay, so how could I find my modulus from 5 minus I?
X plus y, x squared plus y squared.
Yep, exactly. So it'd be the square root of
X squared
5 squared.
plus 1 squared.
Yeah, negative
Minus
1
1
squared. Yeah, exactly. It's just the real part squared plus the imaginary part squared. It's just Pythagoras, right? It's just Pythagoras. So what is 5 squared?
26 root 26.
Yeah, okay, so 5 squared is 25 plus negative 1 squared is 1, so it's the square root of 26. And I would leave my answer like that. And what about my theta? How can I find my theta?
Theta. Tan inverse.
Good.
1 minus 1 over
Yeah, exactly. It's negative 1 divided by 5. Okay? And if you stick that in a calculator, what does it come out as in radians? Negative 11.3, is it? Radians. Okay? Must be in radians. Okay. Why does that come out as negative? Yeah, good. Think about where it is on the complex plane. So 5 minus I, that's 0. It means move 5 in the real direction, so it's over here at 5, and then move 1 down in the imaginary direction. So it's this point down here. And you remember that by definition, we have to move anti-clockwise from the positive real axis. So all the negative means is move in the opposite direction, move in the clockwise direction. So that distance in there. Yeah? Okay, so clockwise is moving in the same direction as a clock. Okay, anti-clockwise is moving in the opposite direction. So by definition, when we measure our angles in complex numbers, we move anti-clockwise from the positive real axis. In other words, we move in that direction. Okay, so all the negative means is I can't be bothered to go all the way around and then get back to there. I'm just going to go clockwise. Okay, so clockwise is moving in that direction, same direction as a clock.
Like what?
Like a watch. Yeah, you imagine an analog watch. So clockwise means move around that direction. Anti-clockwise means move in the other direction. Yeah? Okay, good. So in other words, if I was going to write 5 minus I in polar form or Euler form, let's go with polar form, it would be my r, which is root 26, times by the cosine of my argument, which is negative 11.3, okay, radians, plus I sine of my argument, which is a negative 11.3. Is that okay? Yeah. So therefore, when I'm finding z squared, nice and easy then, I just take my r and I square it because I'm stretching the whole complex plane by a factor of root 26 twice. So it'd be root 26 to the power of 2, times by the cosine. Well, effectively, because I'm moving the entire complex plane by an argument, by an angle of negative 11.3, then because I'm raising it to the power of 2, I'm doing that twice. So it would be 2 lots of negative 11.3 plus I sine of 2 lots of negative 11.3. Okay, and then I just tidy it up. So I get root 26 squared is just 26. And I get cosine of negative 22.6 radians plus I sine 2 times 11.3 is, sorry, 2 times a negative 11.3 is 22.6 radians. Like that. And that's your final answer. Okay? So actually the way we should deal with working with powers of complex numbers, it's actually really straightforward. Okay? You just take the modulus, raise it to the power of n. You take the argument and you're multiplying by n. And then you do that as many times, then really just simplify. Just simplify there. Okay? But it needs to be in either polar form or Euler form to start off with. Otherwise, you can't do anything with that because you need to know your modulus and you need to know your argument. Okay? But I mean, I didn't want to just give you the formula there. I wanted you to kind of work with what it actually means geometrically. Do you remember what it means geometrically if you go back to your multiplication argument? When you're multiplying by complex numbers on the complex or argand diagram, then effectively you are doing this stretch. So you're stretching the entire complex plane. That's not a surprise because with real numbers, you are literally stretching the entire number line. It's just now you're stretching the entire 2D complex plane. And you're also doing this rotation as well. Okay? So when you raise it to higher and higher powers, you're just doing exactly the same as that. So you're stretching and you're rotating, but you're doing it however many times you're raising the power to. Okay? Hence why you get this formula. Hence why you get this formula. Okay? It's just a stretch and a rotation. That's all it is. Okay?